In this video, we're going to take a look at inverse functions, particularly determining if two functions given as graphs or equations are inverses of each other. And we're going to calculate an inverse of a function, whether given an equation, a set of ordered pairs, or a graph. So let's just jump right into it. An inverse function. We're going to let f of x be a function. That's your typical function notation. The inverse function to the function f interchanges all ordered pairs. So the x's become y's and the y's become x's. You see, function f of x has ordered pairs x, y, where f inverse of x, the inverse of function x, is going to have ordered pairs y, x. So we just switch all of the x and y's. So we take a look right away at the steps to find an inverse given a function. We replace the f of x with the y, then switch all of the x and y's to finally solve for y, and then replace y once it's isolated with this function notation, which is read f inverse of x. It looks like f to the -1 power, but it's read f inverse of x. So with those steps in mind, we'll jump right in to find the inverse of function f given a set of 3 ordered pairs. Well, there is no variable x and variable y in an equation to be able to switch and solve for. So literally we're just going to interchange all of the x and y ordered pairs. So 4, 1 would be a point on the inverse, and 8, 2 would be another point on the graph of the inverse, and 12, 3. The domain of the original function is the list of x values, or the set of x values, 1, 2, 3. The range is the set of y values, 4, 8, 12. Now when we look at the inverse function, we see the domain now is the x values, which are 4, 8, and 12. Oops, brace. You'll notice the domain was the range of the original function. That's now the domain of the inverse. And so the range of the inverse is actually going to be the same as the domain of the original. The y values over here are 1, 2, and 3. It's important to point that out because, as we've said in the definition of inverse functions, that we interchange the x and y's in the ordered pairs or in the equation. Here, that would also mean, as you can see, that the domain and ranges switch since they involve x and y. Given an equation, the steps are the same. We're going to switch x and y. So this is going to be 3y equals x. I have replaced the x with y and replaced the y with an x. I also happened to, by choice, write the equation with the y on the left side. This way our answer will look a little nicer. Anyway, now we solve for y, so divide both sides of the equation by 3, and y equals x over 3, or 1/3 x. You can replace with the inverse function notation. F inverse of x is going to be x divided by 3. The domain of the original equation or original function 3x is all real numbers, as this is a line with a positive slope of 3. Its range is also all real numbers, as there are no values of x that would be undefined. We switch the domain and range as we move to the inverse function. Again, that is also a line with a positive slope. This time it's a slope of 1/3 as opposed to 3, but the domain and range is still negative infinity to infinity, or all real numbers. Another equation to take a look at: y equals 4x plus 7. We're going to switch x and y. X equals 4y plus 7. Here I've written the equation in a way that you might be more comfortable with to get started. And then we solve for y. So subtract 7 from both sides. X minus 7 equals 4y. Divide both sides of the equation by 4. And personally, I like to divide every term individually by 4 in case, the x over 4 would simplify, or the negative 7/4 would simplify. In this case, it does not, but f inverse of x is best written as x over 4 minus 7/4. Both of these are linear equations. There are no restrictions on x or the values of x. So again, the domain is all real numbers and the range the same. All real numbers, or negative infinity to infinity. And that's for both of these functions. So it's because the domain and range is the same on both, it's harder to see that they are in fact interchanged, the domains and ranges, like you saw in the first example. So we've looked at inverses when given ordered pairs. We've looked at it when given equations. Here I'm going to give you the set of ordered pairs, but in a table. So you could be even given a table and get this taken care of. So let's go ahead and graph these points, and then we'll look at inverse functions graphically. So 3, 1, 1, negative 2, and negative 1, negative 5. Go ahead and put a scale so that we know we're counting by ones. I've labeled the x and y axis. I've plotted my points. We are good to go. Graph the function. We've just done that, and now it's inverse. So before we switched x and y's. So now my table is going to be y x. And this y will be the new x, and this x will be the new y, right? So this column becomes the new y's, and this column becomes the new x's. So 1, 3, negative 2, 1, negative 5, negative 1. Negative 5, negative 1, negative 2, 1, and 1, 3. And maybe I'll do a different color, orange. So we'll do the inverse in orange so that it'll stick out a little bit more. And this is now the orange x and the orange y, the old x and y's when switched. As you look at this graph, answer this question. The inverse is the reflection of the image over what equation? So what line is the reflecting line here on the graph? And then what is its equation? you should see this line as the reflecting line. I'll put that as a dotted line, where the distance from each point to the dotted line is the same from original function, looking at the corresponding point on the inverse function. So that is the reflecting line, and its equation, y equals x. So inverse functions are reflections over the y equals x line. And we'll see a couple other examples, I believe, of that. A question to ask ourselves here is, are all inverses of functions themselves? And the answer to that is sometimes, but not all. And some more general information to kind of help unpack that for you. A function has an inverse function if that function is what we call one-to-one. A one-to-one function means that each x value corresponds to only one y value, and each y value corresponds to only one x value. You'll remember from the last unit that each x value corresponding to only one y value, in other words, the x's will not repeat, that dictates or indicates that we have a function. But the inverse is a function if each y value corresponds to only one x value. That would be the inverse function. This means if two functions are inverses of one another, the x values and y values are interchanged, as we've already explored. And then a function is one-to-one if it passes a horizontal line test. So if a horizontal line passes through the original function no more than one time, then the inverse will be a function. The vertical line test on the original will indicate whether or not the original is a function to begin with, but the horizontal line on the original will tell us if the inverse is going to be a function before I've even graphed the inverse. So as you take a look here, here's another example of looking at inverses on a graph, and you can see that they would be reflections over this y equals x line. As I graph that on both graphs, these would be inverses of each other graphically. The vertical line test on this original function would show me that this original parabola is a function. Drawing a vertical line, it crosses only one time. But if I was to draw a horizontal line on the original function, I see that it crosses two times. This means that its inverse is not a function. If we find the reflection of this original function, or parabola in this case, we find its reflection over the y equals x line and graph the inverse, I could test the inverse itself with a vertical line and see that it crosses twice, and that would therefore fail and not be a function. So you can still use the vertical line test as long as it is on the inverse to determine if the inverse is a function or not. Or right from the beginning on the original function, we can run a horizontal line test to know. So as you take a look at these two graphs, without graphing the inverse, let's determine if the inverse will also be a function. A is a function. It passes the vertical line test. Its inverse will be a function because it passes the horizontal line test, crossing only once. Yes, inverse is a function, making the original function what we call 1 to 1. And we know this because it passed the horizontal line test. Letter B passes the vertical line test, so this graph is a function, but when we draw a horizontal line, it crosses 4 times. So the inverse is not a function, since this fails the horizontal line test. I want to take a minute and go back to review composition of functions that we looked at in the last video. And let's find d of f of x, given function d of x to be 4x minus 2, and function f of x to be 1/4 x plus a half. So d of f of x, which was 1/4 x plus 1/2, and we take that whole function f and substitute it in for x in function d, which is what this notation will hopefully help you with. So 4 times the quantity 1/4 x plus 1/2 minus 2. We'll distribute 4 into the parentheses here, and 4 times 1/4 is 1x. 4 times a half equals 2, and then subtracting 2, and 2 minus 2 leaves us with just x. So that's cool. And then over here they want us to find f of d of x. So the function f of the function d for x minus 2 of x, and that will be now substituting function d in for x in function f. 1/4 times 4x minus 2 plus 1/2. And similarly to the last, we'll distribute a 4th, which gives us 1x minus 1/2 plus 1/2, which leaves us with just x again. Well, that's interesting. We got the same answer from both. And more importantly, both were the same, but they were also x. So you should see that both resulted in an answer of x. Which leads us to the inverse function theorem. The inverse function theorem says that if two functions, f and g, are inverse functions, that's true if and only if, for all x in the domain of f, g of f of x equals x, and for all x in the domain of g, f of g of x equals x. Basically, if I form the composite of the inverse, the function of the inverse, and the inverse of the function, and get x both times, then the two functions would be inverses of each other. So we're going to find the inverse of h of x and then verify algebraically using the inverse function theorem that they are actually inverses of each other. Kind of a way to check our work. So as we go back to the original steps that we had looked at to find the inverse of a function, we're going to replace h of x with y. Then we're going to switch x and y and say x equals 3y plus 5 over 4. Now we solve for y. So I'm going to multiply both sides of the equation by 4. And 4x equals 3y plus 5. Subtract 5 from both sides of the equation. 4x minus 5 equals 3y. I'll bring my work up here. Divide everything by 3 and have 4x over 3 minus 5 over 3 equals y. And then substitute h inverse of x in for y to give us our function notation again. 4x over 3 minus 5 over 3. I'd like to verify algebraically, so I'm going to do h of h inverse of x, which is going to be 3 times 4/3 x minus 5/3 plus 5 all over 4. Distribute the 3 and I have 4x minus 5 plus 5 all over 4. Combine like terms in the numerator and I just have 4x over 4. 4 divides by 4 to be 1, leaving me with just x. I've run out of space here, but let's try up here. We will find h inverse of h of x going the other direction, which would be 4/3 times 3x plus 5 over 4 minus 5/3. When we multiply the first two fractions, the 4's will simplify, and so we will have 3x plus 5 all over 3 minus 5/3. And in simplifying this, 3 divides by 3 to be 1, leaving me with x. The 5/3 minus 5/3 goes away to 0, so I have just x. And since h of h inverse of x and h inverse of h of x, so forming the composite both ways, yielded an answer of x, we have proven or verified that the original function h of x and h inverse of x, as we found, are actually inverses of each other. So we have verified algebraically our work was correct. Okay, the last question we're going to look at here is given function f as 3x plus 2 and function h as 1/3 x minus 2. We want to determine if these are inverses of each other. Tell me why or why not. Show graphically and algebraically. First, algebraically, f of h of x. If these are inverses, that should give me an answer of x. So f of 1/3 x minus 2 equals 3 times 1/3 x minus 2 plus 2. We'll distribute 3 and get x minus 6 plus 2 gives us an answer of x minus 4. That is not equal to x. So right now, if my math is correct, my algebra is correct, these are not inverses. But let's just double check by finding h of f of x. And if that one yields an answer of x, we might go back and check our work. So this would be h of 3x plus 2. And that's going to be 1/3 times 3x plus 2 minus 2. Distribute 1/3 and we have x plus 2/3 minus 2, which would be 6/3. When we do that subtraction, we have x equals negative 4/3. I'm sorry, x minus 4/3. My mistake. This answer is also not x, so we have shown algebraically that these are not inverses. Now let's look at these graphically. I have, come on, I have graphed these functions. This one that is in red is f of x. Let me write that in red. F of x, and in blue is h of x, and the dotted black line here is the y equals x line, which should be the reflecting line if they are inverses. So if they are inverses, they're reflections over that dotted line, but you can see the intersection point is not on the line, which is a good indication that they are not reflections of each other over that line. Although they look like reflections, the slopes are inverses, or are reciprocal slopes, so they do reflect, just not over the y equals x line, therefore graphically are not inverses either. Hopefully this video has been helpful for you as we've begun to explore inverse functions.